Hey everyone, my name is Sohan Maheshwar. I'm a dev advocate at Fermion, and today we're going to show you how you can build a serverless WebAssembly app using Python with this open source framework called Spin. Now, if you're not familiar with what WebAssembly is, or if you're not familiar with what serverless is, no problem, that's what I'm here for. And by the end of this session, hopefully you'll know how you can get started with WebAssembly. I'm going to start off with a very bold claim, and that is the next wave of cloud computing will be powered by WebAssembly. And this is a rather bold way to start off a session. So hopefully by the end of the session, you are convinced as well. In fact, the creator of Docker, Solomon Hykes, had tweeted something to this very effect about 2 or 3 years ago. And in a few slides, I think you will see why. So today we're going to talk about what WebAssembly is, how it works, when to use it, and how this will potentially change cloud computing. I'm also going to show you 2 demos, very hands-on, going with the hello world example to an example of AI and how you can actually use this. So stay tuned till the end for both of these demos. So first things first, I always have to context set. What really is WebAssembly? The boring answer is it's just another bytecode format. Now, the short history behind it is sometime in the 2010s, there was this technology introduced called WebAssembly, originally meant for the browsers. It was meant to be faster, it was meant to be portable, it was meant to be more lightweight. And even now, companies like Adobe, Figma, Shopify, all of these companies use WebAssembly in their browser. Now, if I say wasm, it's just another word for WebAssembly, short for WebAssembly basically. And really how it was designed was for it to be a portable compilation target, which means any WebAssembly module could run anywhere, right? Any architecture, any OS, any system, as long as that system could run a particular WebAssembly runtime. Now, what does that mean? Well, a few of you all might be familiar with the Java world and how JVMs worked, or Java virtual machines worked, where essentially you wrote a Java program and this compiled to something called Java bytecode. And that Java bytecode could be executed in any environment which could run a JVM or a Java virtual machine. And these JVMs could run on ARM processors, on x86 processors, on Windows, Mac, Linux, whatever, right? So it was fairly portable. Now, wasm was designed with a similar method in mind, similar idea in mind, but instead of just sticking to one language, you can write a program in any language. Yes, so you can write it in Rust, C++, JavaScript, TypeScript, Zig, Go, and of course Python as well, which compiles to something called a WebAssembly bytecode. Now this WebAssembly bytecode is the new format that I was talking to you about. It is a wasm module, and that could be executed anywhere that has a WebAssembly runtime. And this runtime, like I said, could be executed on ARM, x86, Windows, Mac, Linux, Raspberry Pi, Kubernetes, whatever, right? So you can write code in any program. So that essentially is WebAssembly. A couple of more things for you to know. Like I mentioned earlier, it started off in the browser, but sometime in the late, I think 2010s, around 2017, 18, there were calls to say, hey, this might actually make sense if you could run it on the server side as well. So we'll talk about that very soon because that's our focus for today. And the whole idea really is compile once and then run that code on any number of targets because it is so portable. Now, how does this really work? How does this compile once type thing really works? So you need to know some basic terminology. So when I say a wasm module, we use the words guest and host. So a wasm module essentially is that WebAssembly program that you wrote. You wrote a program in some language which converted it into a wasm module. So for instance, you created a function to add 2 numbers or to increment a number by 1, right? So that is a wasm module. Now, the theory behind WebAssembly is it's secure by default, or it's sandboxed by default, which means no other WebAssembly module, no other HTTP request, nothing can access this module by default. Now, this module runs in something called a runtime or a host. And even this host can run multiple modules, and for one wasm module to access something in another wasm module, it cannot unless given explicit permissions to do so. Right? There are some things, we don't need to get into the weeds of some things like shared memory and all of that, but the analogy that I want to draw here is, think of a guest wasm module as like a room in a hotel that you're staying, and the host runtime is the hotel itself. Now, as a guest, you have access only to your room, not to the other rooms, of course, but there are some things that are shared, like say the gym or a restaurant or a lounge within that hotel that, you know, other guests can also make use of. So that's the analogy that you can think of. So essentially, with this compile and run, you write your code in any language, which is then compiled to a WebAssembly or a wasm bytecode format, and this can run in any place that can run a WebAssembly runtime. So think of it as a virtual machine that can run, you know, a WebAssembly runtime. Now, we said that it originated in the browser, right? And because of its lightweight, because of its performance, because of its security, everyone's like, hey, hold on, this actually might make sense if you want to run it in the server side as well. But guess what? For something to run on a server, you need access to things like files. You need access to things like sockets, system clocks, random number generators, and so on. So in the late 2010s, this thing called wasi was introduced, which stands for WebAssembly Systems Interface, which essentially enabled you to run WebAssembly on the server side. And quite frankly, this was a big turning point towards the shift of how WebAssembly can change cloud compute. The TLDR, of course, is you can now run wasm outside of the browser. Bowser is a Mario character, but essentially you get access to several operating system-like features, right? So access to files, clocks, random number generators, all of the things you need to run on a server. The cool thing is it retains wasm sandboxing, but it also includes input-output. So unless you give it explicit permissions to access a file, or for a file to access this module, it is security sandboxed by default. And the good thing is, browser is not needed. So it doesn't depend on a web API or JavaScript, because, you know, we're all Python fans here. If you take a look at the top 20 languages according to RedMonk's ranking, a chunk of them, actually most of them except things like CSS, of course, or PowerShell, have support for WebAssembly, right? So everything from JavaScript, Python, Ruby, TypeScript, all of that. And across things like core WebAssembly, browser, wasi, and even Spin, the SDK that I'll be talking about in a bit, have access. And this is in a continual state of evolution where there's even more language support coming in day by day. So the question is, I think, how do I compile my code to WebAssembly? I know to write code in Python. I know to write code in Rust. What's actually happening? Now, the thing is, with compile languages like Rust or C or C++, it actually is a much easier process, right? Rust, for instance, has amazing WebAssembly support, because with Rust, you compile it to a WebAssembly module, which can execute on a WebAssembly runtime, wherever, right? Similar to how we spoke about. Now, this is a compile language, so it's already low level in that sense. But with interpreted languages, these are a little more tricky, because with languages such as JavaScript and Python, you are writing code which are then interpreted to something that's at a lower level, which can then run, right? Like bytecode. So here's a nice piece of trickery that actually happens where you write a program in Python that's compiled to WebAssembly, that's executed on a WebAssembly runtime. So if you take a Python program, but that needs to be interpreted. So what actually happens is a bunch of very smart and knowledgeable people have provided the Python source code, like CPython, for instance, in a WebAssembly format itself, which is then sort of compiled along with your program into WebAssembly, which then runs on the wasm runtime. Now, this sounds complicated, but the good news is you don't have to worry about how any of that works. If you want to build a program in Python that converts to WebAssembly, all you have to do is do the Python bits, right? And this particular step of this compiling the interpreter to wasm is actually done by hand. So a bunch of smart people are doing this by hand. They're testing it out so that devs such as us can can actually just focus on writing code in Python. So that's how interpreted languages actually compile to WebAssembly. Spoken quite a bit, and I don't think you've seen code so far, so I'm going to get to code very shortly. How do you get started with building your first WebAssembly app? So I'm going to use this open source project called Spin. Now, Spin is the open source tool for building WebAssembly and serverless apps. Check it out on GitHub. You can create a new serverless app with just 3 commands, I promise, right? And you can even deploy it in the cloud with the 4th command, and I'm going to show you how. It's completely open source, so if you like to contribute to open source, go ahead and do so. In fact, there is a bot called the Good First Issue bot, which gives you good first issues that you can get started with, contributing to Spin. It supports 15 plus programming languages, a very simple CLI and developer experience. We have 4.6K stars on GitHub. We also have a Discord channel and things like that. So feel free to jump in. I think it's a nice community. So yeah, you can do that. And again, just to give you a sense of what Spin is, completely open source, and it's built with open standards, supported by the Bytecode Alliance. At a glance, you get the dev experience around building WebAssembly apps on the server side, but you also get things like writing serverless AI, you get a key value store, a CLI, and also a SQL database that you can use, right? And you have different triggers for this, and we will talk about it very shortly. So again, enough of me talking. Maybe let's dive straight into the demo. All of this can be found on developer.fermyon.com/spin. And like I said, it's completely open source. So I'm going to open up my terminal right here. Yeah. All right. So I've installed the Spin CLI already. And I'm just going to start off with the first of the 3 commands. Not spim, but Spin. I said 3 commands, so this is the first of those 3 commands, which is to create a new Spin app, right? We're creating our first serverless web app using Python. Now, you will see there are a bunch of templates for you to get started. And on the left are triggers, right? Typically, triggers are things like HTTP, because with serverless, it's completely event-driven. Or you can also have triggers such as a Redis, which is a Redis database, right? So right there. On the right, you will see a bunch of languages like C and Go and Python and Rust. So those are the different languages for you to get started to write those WebAssembly apps. We are talking about Python today, so I'm going to go ahead and say HTTP Python. I'm saying hello world Conf42. All right, skip the description. There's something called HTTP path, which you can specify a URL upon which your app will be triggered, right? So say /checkout will trigger a certain module, or /add to cart will trigger something else. Here let's leave it as default, which means anything to that URL will give you or will trigger this app. So I'm going to hello world, I'm going to cd into this directory and then just open it in VS Code, and let's see how that goes. All right, so a Spin app is fairly simple, and the entry point to the app is this thing called an app manifest, or a spin.toml. Now you can see some metadata here. You don't have to worry about that. This is the trigger that we added, where we say here by default, hit this particular component, which the code to which we will be writing very soon. And there is some description of that component as well. So you can see the .wasm file, and you can see the command to convert it from Python to wasm using this thing called py to wasm. Again, we as developers don't have to worry about how py to wasm works. We just know that some people have created this py to wasm, and we can focus on writing our Python code. Now, serverless is completely event-driven, right? So you get a request and you have to send a response. Now, this is the simplest hello world possible. So there is a request coming in. We are sending a response of 200K saying hello Conf42, right? And I'm going to save that. Now we added our first command, which was spin new. I'm going to build my program by saying spin build, right? You can see how fast that was. I haven't sped up the video or anything. That was literally it. And now I can just say spin up which is to test the app locally. Now, this is part of a good developer experience where you can test something locally before pushing it to the cloud. Oof, my pronunciations today. So I can just do a simple curl to this. Oops, curl minus I. Sorry, I'm just going to do that again. I'm going to do a spin up so that it's running locally, right? That's spin up running locally. And I'm just doing a curl command, curl minus I, right? And as you can see, the response returned is hello Conf42. So in 3 commands, we went from nothing to creating an app that is running locally. And it's a serverless WebAssembly app written in Python. The cool thing is with the 4th command, I can deploy this to the Fermyon cloud. So actually have this app that's running in the cloud for anyone to access. Now, how this essentially works is it takes that particular wasm file that has been created, which I'll show you now, and it pushes it to the cloud, right? So if I do, let me do ls, you can see ls, if I do ls minus la, you can actually see an app.wasm that's created here, which is about a couple of megabytes. And if you do a nano app.wasm, you will see the bytecode format, which for us, it's mostly gibberish, right? It doesn't make sense, but that's essentially what the WebAssembly runtime is reading. So it's deployed to the cloud. In fact, I can go to this website right now and I will hopefully be able to see the output, right? There we go. You can see hello Conf42. So like I said, in 4 commands, we have gone from nothing to deploying an app in the cloud in hardly any time. Cool. So let's get back to this. So 4 things that make WebAssembly great, right? So the first one is binary size itself. Why is WebAssembly a big deal? Why is it going to be the next wave of cloud compute? Well, at scale, things like binary size makes a big difference because that changes your deploy times, it changes your startup times, it changes your carbon footprint. There was a benchmark done in Rust, and Hello World was just about 2 MB. And an ahead of time compiled Rust WebAssembly app was only about 300 KB. We just saw in our demo as well, the app.wasm file was about 2.5 MB, which was a simple file. So these are very, very small apps, right? The same thing using, if you're running it in Flask, say on Docker or something, is a much bigger file, right? So WebAssembly is lightweight and it's designed to be so. Startup times are comparable with natively compiled code. It's not the same, of course, it's going to be slightly slower. Again, with Rust, it was about 2.3x slower than native, but those are near native compile times, which make a lot of sense, especially when you're building at scale. We mentioned earlier about how WebAssembly is portable, which means you can build this once and run it anywhere. That app.wasm will run on any runtime which supports WebAssembly, right? So the same just-in-time build will work across operating systems, platform architectures, different systems, and so on. And like I mentioned, it's designed to be security sandboxed by default. So the approach is a very capability-based security model. Any HTTP request going in or going out or coming in has to be explicitly given. Any access to files in or out, again, has to be explicitly given, which makes this very secure by default. When I said the next wave of cloud computing will be powered by WebAssembly, how will this change? Yeah, sure, it has all these cool things, but how will this really change cloud computing? Well, my prediction is, and I've been working a lot with emerging tech for the last 10 years, is that it will change things gradually and then suddenly, right? Because there are so many things that we are seeing in how cloud computing is evolving right now. If you see the evolution of it, we've gone from a pre-cloud era where, we had this server running down the hallway in this room that was cooled by multiple air conditioners, where you had to take care of everything from the hardware to the security, the physical security, but to the kernel, the drivers, the operating system, and of course, your app. Good old days, we don't want to go there anymore. As we evolved towards things like virtual machines, we saw, where the physical security and the space we didn't really need to care about. A cloud provider gave that to us. We could focus on things like our app, but also we had to take care of updating our OS and the security and our utilities. That has changed a bit with containers, and now that is changing with serverless, where you can focus only on your business logic and your app. You don't need to worry about scaling up, about scaling down, about updates, any of that, right? The host takes care of most of that. You as a dev focus only on your business logic. So talking about how that changes containers, how that changes cloud computing, we won't see any more clunky containers. I'm sure we're all familiar with things like Docker and Kubernetes. These are widely used in enterprises, in startups, wherever, right? And it's a known fact that with containers, there is a huge underutilization of resources that actually happen. So, even in a study of the top 50 public software companies, it's estimated about $100 billion of market value is lost because of the cloud impact on margins. What this basically means is when we're provisioning for cloud computing space, we typically provision for the peaks and not the average, right? We're like, hey, what if there is so much usage on our app? This is the peak usage on our app that happens once a month. So we have to provision for that much. But guess what? Your average usage is way below, and that's what's running most of the time. So there's all of these resources that are being underutilized. With WebAssembly, you can actually scale to 0 in no time, right? You can scale up and scale down in no time, and it's so lightweight. So you can pack a container with far more number of apps than you're doing currently, thereby utilizing your resources better. And as a company scales, or as you deploy more and more apps into a container, this starts making a lot more sense, right? We're talking about, again, running in the cloud at scale. You start saving costs, you're faster, you're more agile, you can, do things quicker as well with microservices. So this starts making sense again. So WebAssembly is going to change this part. And the second is it could potentially fix serverless as well. Now, serverless is gaining a lot of traction in the last few years with services like Lambda and Azure Functions and so on. There are a few problems that I see with things like serverless. One is, of course, serverless in the public cloud has a cold start problem. If you're not familiar, basically how serverless works is there is an event that goes to a function that's running somewhere, and then that program starts, executes, and then sends a response back. But with how services such as Lambda and Azure Functions are actually structured, there is something called a cold start time, which means there is a finite amount of time between the request being sent and the program actually starting up. And it could take even about 2 to 3 seconds with AWS Lambda, but typically we see maybe about 500 milliseconds as the cold start time. This is not ideal for many use cases where speed is of the essence. And people have like complex and expensive workarounds by warming up an instance by sending pings once in a while, which these costs are borne by you as the customer, right? So that's not just coding complexity, but also costs. With WebAssembly, you can actually, because of its small size and its fast startup time, we are actually able to cold start a module on every execution in just about 2 milliseconds, right? So that is a significant difference between, say, an AWS Lambda. And again, this is due to the properties of WebAssembly as well as our tech stack, where we're able to do this and then scale it down back to 0. So if your function has run something, that's all you're charged for. So broadly, these are a couple of ways that the cloud will potentially change with the adoption of WebAssembly. I did promise you 2 demos, so I'm going to show you another demo and this time the usage of serverless again, but again using AI. So LLMs, or large language models, are the talk of town. Everyone's talking about it. So I did say Spin gives you access to LLM as well. We have access to the Llama 2 language model, right? And again, with just like 5 lines of code, I'm going to show you a simple Hello World-ish app, but that one that is actually using AI. So I've written the program already, right? It's pretty simple. All you have to do is import a couple of libraries, especially Spin LLM. And again, remember, we're doing this serverlessly. So request comes in, request goes out. Now we have to call this function called LLM infer and mention the large language model, which is Llama 2 chat, followed by the text itself. So I'm just saying, can you tell me a joke about cats? Have no idea what output this will send. And if it's successful, it'll actually return the text. If there's an error, it'll return the error. So 10 lines of code, but really it's like 2 lines of code that you need to know, right? It's literally that simple. The one small change to your spin.toml from earlier is I mentioned the AI model that I want to speak to. This is cool because as and when we have support for different models, you can just swap this out for a different model name, or potentially even bring your own model, and you don't have to like recreate everything from scratch and so on. So I'm going to go back here and do the same steps again. Remember, just spin build. And now I can run this locally, or I can run it in the cloud. This is using a large language model though. So if I run it locally, it can take about, 10 minutes to actually process it because I'm running it on a MacBook. There is a pretty cool plugin that someone's written for Spin where you can run this program locally, but talk to a large language model that's running in the cloud. So I'm going to do that. I've done one step of a runtime config, but let's open the browser and see how this goes and see if it's fast as well. I'm hitting enter now. And in maybe a second or two, yes. So there we go. These are the cat jokes. Why did the cat go to the vet? To get its positive diagnosis. What did you call a group of cats playing instruments? A musical band. Well, I didn't say the jokes are good, but well, it is a joke. That's what the AI decided was funny. So who are we to judge? Again, this is completely serverless. I didn't need to have a large language model running on a server in the cloud consistently, right? It made a request to a large language model that processed it, sent a request back to me, and that's it. Again, you saw the speeds, the scale up and scale down, and this is just the tip of the iceberg. The one thing that I'm super excited about in the WebAssembly and serverless WebAssembly world is something called the component model. So software, when we build software now, the process itself is kind of weird because, for instance, you're writing an app in JavaScript and you need 2 things. You need a YAML parser and a date formatter. But guess what? There are no great YAML parsers in JavaScript. There are no date formatters, great date formatters in JS. So you write your own, right? Or you write one, or you use one that is not very good. Basically, it's very inefficient. But there are great Rust YAML parsers because Rust is very good at parsing lots of data, and Python's very good with numbers. So there's an amazing Python date formatter. So what if there was a way for you to, in your JavaScript app, use a Rust YAML parser and a Python date formatter? Well, with the component model, which is live and you can try it out, this is actually possible. The idea is all of these languages convert to a WebAssembly module. So if you define an interface that allows you to talk to interface where these modules can talk to each other, then you can theoretically have an app composed of different modules in different languages. And it's not just theory, because there are enough examples now of languages written programs written in different languages. So you could write something in Rust, Python, C++, which would compile to a WebAssembly module and talk to each other. And you could compose an application this way. So you have a component A, which has a core WebAssembly module, which exports a function, and component B wants to import that same function. So you can join the two together. They can be in Rust, Go, Python, whatever, and thereby you create a new component called C. So this is possible now, and as unbelievable as it sounds, it literally is possible. You should check it out. With Python specifically, I want to shout out the work done on something called componentize-py, which is a tool to convert a Python application to a WebAssembly component, right? It takes something called a WIT file, or a wasm interface type file, which determines the imports and exports. It takes the name of something called a world, which is, it's a very abstract concept, but a place where these imports can export and those exports can import. It takes the name of a module, which targets that world, and a list of directories in which you can find this module. It's super fascinating. Few people who work at Fermyon have contributed to this, and again, it's completely open source, so check it out. It's part of the Bytecode Alliance on github.com/bytecodealliance/componentize-py. All right, that's it for my presentation today. I think I just about made time. Feel free to join our Discord server or get started with Spin. I'd love to, see what you're building with WebAssembly. We do a lot of cool stuff on YouTube and Discord, so join us there. Feel free to connect with me on LinkedIn if you like this presentation. Hope you learned something new today, and I look forward to seeing what you're building with WebAssembly and Spin. Till then, enjoy the rest of the conference and see you soon.